Today we're going to go through and talk about piecewise functions. So our learning goal for today is I can evaluate and graph piecewise functions. So we're going to start here, right, talking about like what exactly is a piecewise function. So it turns out a lot of times a function cannot be described with only one equation. It requires more than one equation. And so on different parts of the domain, for different x values, you have different equations that describe it. So when you have one of these functions that are made up with, for more than one equation, that's what we call a piecewise function. So if you look down here, right, and this is the important part that I have in my notes here is it says a piecewise function is a function defined by two or more equations. Okay, so a function that is defined by two or more equations. So here's an example of a piecewise function. Right? It says f of x equals x minus 2 when x is less than or equal to 0. Or you have this other part, right? It says f of x equals 2x plus 1 if x is greater than 0. So if you look over here at the graph, right? When x is less than 0, on the left side of the y-axis, we have that equation, right? It matches with the first part of the piecewise function. Whenever x is greater than 0, you have this equation over here, okay, that matches with that one. Okay, so that's kind of like what a piecewise function looks like. Again, it's defined differently depending on different parts of its domain. Okay, let's do an example so you can kind of see. We're going to start by evaluating. Remember, if you evaluate a function, it means you're plugging numbers into the function. So look down here, I have this piecewise function. It actually has three different parts. Right? F of x equals 3 when x is less than negative 2. It equals x plus 2 when x is between negative 2 and 5. And it equals 4x when x is greater than 5. So again, this part over here, these are just the constraints. It tells you when to use each part. I use y equals 3 when x is less than negative 2. I use f of x or y equals x plus 2 when x is between negative 2 and 5. And I use 4x when x is greater than 5. So those parts I just highlighted there are just the constraints. They tell you when to use each equation. Okay, so let's start. So I got this f of negative 8. So if I'm going to plug negative 8 in, I've got to decide first of all which of the three parts to use. So what I'm asking myself is negative 2 less than is negative 8 less than negative 2? Is negative 8 between negative 2 and 5? Or is negative 8 greater than 5? Well, negative 8 is less than negative 2, so that means I use this equation right here. So if I plug negative 8 in, there's no x value. So if I plug negative 8 in, nothing changes. It just equals 3, no matter what. Let's try this next one. So what happens if what is f of negative 2? It's going to come up here as negative 2 less than negative 2. That's not true. Is negative 2 greater than or equal to negative 2? It is. Because that one has the equal sign, that means I'm going to use this equation right here. So just plug in negative 2. So f of negative 2 equals negative 2 plus 2. So f of negative 2 comes out to be 0. Okay, let's try f of 0. So again, pick the right equation. So 0 less than negative 2 is 0 between negative 2 and 5, or 0 greater than 5. Well, 0 is between negative 2 and 5. So we're going to use that second equation. So if I plug 0 in, I get 0 plus 2. So f of 0 is equal to 2. So you got to pick the right equation out of the three, and those highlighted parts are going to tell you which one to pick, and then plug it in. Hey, f of 3 is between negative 2 and 5 again, so I'm going to use this second equation again. So I'm going to end up with 3 plus 2. So f of 3 is equal to 5. Let's try f of 5. So again, 5 is a tricky one, kind of like negative 2 was, because I've got a 5 right there and a 5 right there. So this one says, is 5 less than or equal to 5, or is 5 greater than 5? Because this one has the equal sign, we're going to use that one. So use that second equation again. So I'm going to end up with 5 plus 2. So f of 5 equals 7. F of 10. 10 is greater than 5, so I'm going to use the last equation. So that'd be 4 times 5 So it comes, oh, sorry, 4 times 10, excuse me. Let me fix that. So it'd be 4 times 10 when I plug it into there, right? So I end up with 40. So when you're evaluating, you have to look at those, at the intervals on the domain there, and make sure you choose which equation is the one you're going to use. Then once you do, you just plug it into the function like you normally would when you evaluate a function, and you should have your answer. So evaluating isn't bad. Most of us do pretty well with that. The one that's a little harder is when we graph. So I'm not going to evaluate this. I'm not going to do that 1 through 4. We're just going to take this function and draw what the graph looks like. So I'm going to give you a couple hints, a couple guidelines that can make this a little bit easier. Okay, so this says f of x equals 2x plus 1. If x is less than 1, it equals negative x plus 3 if x is greater than or equal to 1. So what that means is I transition from this equation to this equation when x equals 1. So what I would suggest first is I would always start by drawing a boundary at the transition. And I know it's switching when x is 1. So I'm going to go to where x is 1 and draw a boundary. This top equation, the f of x equals 2x plus 1, is for when x is less than 1. Well, that's to the left over here, right? When x is 0, negative 1, negative 2, negative 3, I'm going to use that top equation. So right at the top, I'm going to write that down. Y equals 2x plus 1. Okay, and then the right side of the equation over here is when x is greater than 1. So I'm going to put down y equals negative x plus 3. When you have it set up like this, I think it makes it really easy to graph it from here on out. So I'm going to graph y equals 2x plus 1 on this side over here on the left side. And I'm going to graph y equals negative x plus 3 over here on the right side. These are just lines. So when you go to graph a line, you can do it one of two ways. You could use the slope and the y-intercept, or you could do points. I'll do it both ways. So let's start with this first one. Let's do the slope and the y-intercept. So the y-intercept, right? Remember the y equals mx plus b? My y-intercept or b is 1. So I know that's the y-intercept. The slope or m is 2 or 2 over 1. So from that point, I'm going to go up 2 over 1. I could go back. I don't want to go past that boundary, but I could go down 2 and left 1. You know, as many points as I want. And so that's what that half of the graph looks like that. Now, right here on the boundary, we got to decide what's happening, but we're going to leave that for just a second, then we'll come back. Okay, over here on the right side, we want to graph the right side, and that's a y equals negative x plus 3. One thing to be really careful with is if I'm going to use the y-intercept, which is 3, and the slope, which is negative 1 over 1, then I want to make sure that when I use the point 3, it's got to be over here. It's on the wrong side. So what I can do is I can make a point there, but just know that I'm going to erase it in a second. And then the slope is negative 1. So I go down 1 over 1, down 1 over 1. So I can use that, even though the y-intercept's on the wrong side of my boundary, I can use it to graph it. It's just when I draw my line, I'm not going to include it as part of my line. So I'm going to come back up here and grab my eraser, and I'm going to erase that point. So you can use it as a reference point if you want. Now, the other way I could have done it is I could have just gone like this. I could have just done an x, y, and just plugged a couple points in. So I could have started by plugging 1 in. If I plug 1 in there, negative 1 plus 3 is 2. Plug 2 in, negative 2 plus 3 is 1. Plug 3 in, negative 3 plus 3 is 0. Now I plot my points. I got 1, 2, 2, 1, 3, 0. And then once I add those points, I can draw the line too. So I don't care if you use the slope and the y-intercept or the table to graph the line. Either one is fine. Okay, here's the very last thing. We need to decide whether these endpoints, I cannot include them both. If I include them both, then this is not a function. It doesn't pass the vertical line test. So one side's got to be a closed dot and one side's got to be an open dot. So the way I tell is this. If I come up here, x is less than 1. This one does not have an equal sign. So it cannot equal this equation at 1. So if there's no equal sign, I know it has to be a closed dot. So I'm going to erase this point right here. I'm going to come back. And what I do is instead of a closed dot, I just do an open dot up to there. Okay, this one has the equal sign. That means the right side is the one with the closed dot. So that's going to be a closed dot right there. Okay, and there's the graph of my piecewise function. Now be aware that boundary we drew isn't actually part of the graph. I mean, you can erase it afterwards. It isn't actually part of the graph. It's just to guide us as we go through it. And you can leave the boundary there if you want to. But that's what my graph's going to look like. A closed dot there because it's got the equal sign. An open dot there because there is no equal sign. Okay, and then I just graph my two lines. That's what we end up looking like. Okay, so there's one example. Let's do another one. So let's do this one right here. So you want to graph y equals negative x minus 4 if x is less than 0, y equals x if x is greater than or equal to 0. So let's start out with the boundary. So it changes, whoops, sorry about that. It changes from one equation to the other when x is 0. So my boundary is going to be right down the y-axis. That's where my boundary is going to go. Okay, then write equation. When x is less than 0, that's to the left, I got to graph this equation. When x is greater than 0, I've got to graph that equation. Now again, you can use the slope and the y-intercept, or you can use points. Let's try it with points for a second. If I'm going to use points to graph this equation up here, I'm going to start by picking number. I got to pick numbers over on this side. So I could do like -1 and -2, maybe -3, and plug points in. So if I plug in -1, this is a little tricky. It's a -1 makes it a +1, and 1 minus 4 is -3. If I plug in -2, a -2 is a +2, 2 minus 4 is a -2. If I plug in -3, it becomes a +3 minus 4. So I'm going to plot those points. -1, -3, -2, -2, -3, -1. And then we can see the line there. So I'm going to draw that line. Now when I get to that point, I got to decide if the boundaries are going to be open or closed. This one does not have an equal sign. That means I'm going to do an open dot right there. Okay, so it looks like that. So that's using a table. Now, if you want to just say, hey, my y-intercept is -4 right there. My slope is -1. So normally I'd go down 1 over 1, or I could go up 1, left 1. You could also plot it that way, and that's great. Okay, let's graph y equals x. If I plug 1 in, I get 1. If I plug 2 in, I get 2. If I plug 3 in, I get 3, right? It has a y-intercept of 0 and a slope of 1. So I'm going to do a closed dot there. Okay, just connect those. Okay, there's my graph. Hey, the last one I want to show you real fast. This one's a little bit different. It's different for a couple of reasons. One is it actually has 4 parts rather than 2. And the other one is the equations are a little bit different, right? That's just a 1. There's no x there. Okay, let's start by dividing it up, though. So it's equal to 1 as long as x is between 0 and 1. So that first graph goes from 0 to 1. My next graph goes from 1 to 2. I'm going to have a lot of boundaries here. My next graph goes from 2 to 3. So my next boundary is at 3. My next graph goes from 3 to 4. So I've got all these little boundaries. Now each of these, right here, I've got a graph y equals 1. I'll come down here. Right there, I've got a graph y equals 2. And that's my equation is just 2. Right here, I've got a graph y equals 3. And on the last one over here, I got a graph y equals 4. Or y equals 4. So just a quick reminder, when you have y equals a number, it's just a horizontal line. So between 0 and 1, right in here, I've got a graph y equals 1. It just looks like that. All I really have to decide is the open or closed. So I want you to notice with the 0, there's an equal sign. So I'm going to put a closed dot right there. With the 1 up here, there is no equal sign, so I'm going to do an open dot right there. Okay, between 1 and 2, I'm graphing this one, y equals 2. So that's just a horizontal line, and y equals 2. Okay, at the one endpoint, at 1, it's a closed dot. And at 2, there's no equal sign, so it's an open dot. Okay, between the next two, I'm graphing y equals 3. So closed dot, open dot because it's equal and no equals. And the last one's y equals 4. So these are actually pretty easy to graph. because the y equals, it's just a horizontal line. So there's a closed dot at 3, right? Equal sign. There's nothing not at 4, so that's what it looks like. So if I erased all those boundaries, you can kind of see what this thing looks like. This is what that graph comes out to be like right there. Okay, so there is my piecewise function. A lot of times this is called a step function. Is it kind of obvious why, right? Looks like you're going up steps as you go across there. But if you follow those tips, if you always look at your boundaries, draw the boundaries, write the equation that goes in each part, and then just graph each equation separately to make sure it stays within its boundaries. If you do that, then these aren't too bad. Okay, good luck on that.